the first piece of a material which we discussed after the second midterm exam was magnetic force, right? So it was, okay, long ago, almost a month ago. So magnetic force, we introduced two formulas, right? The first one is fundamental force on a charge. You remember charge must move in order to experience magnetic force. So let's assume that we have magnetic field, charge moves with velocity v, and then of course the formula is qv cross b, right? So be careful again with the sign of the charge. Typical place for silly mistakes. If charge is positive, then cross product of v and b gives us the direction of the force. If charge is negative, find a direction of the cross product and then flip it if a charge is negative, right? Careful with that. We will practice. Then if you have a wire with a current, basically a bunch of charges moving in the same direction, right? So again, exposed to the magnetic field B. So in that case, this formula gets modified and it has this form I and then cross product of L and B. Direction of L, vector L, is determined by the direction of the current, right? And the value of L, it's the length of the wire which is exposed to that magnetic field, right? Again, direction of L, it's a direction of the current. Again, subtle point which you might need to remember. So after that, we moved into Faraday's law, production of the induced current, induced potential difference, right, and so on. So Faraday's law. So if you have a loop, okay, now I realized I should have, where is my loop? There it is. So if you have a loop exposed to the external magnetic field, so there is a loop, magnetic field, there must be a flux. If that flux changes, then in the loop there will be EMF produced, potential difference somehow mysteriously, right? And of course, as a result, there will be an induced current flowing, right? So that effect can be described by the Faraday's law. EMF equals to negative rate of change of the magnetic flux, right? And of course, magnetic flux, we're going to use all the time the simplest possible formula when the magnetic field is uniform and surface is flat. Right? So in that case, flux, it's a dot product between B and A. So explicitly B dot A, it's a BA times cosine of angle between them, correct angle, right? And then direction of the current is determined by that minus, and we apply Lenz's rule. You remember every time we analyzed flux, right? Every time in order to get information about the flux, we analyzed... Huh? Say it again?
I think your other mic just started working.
Mic started working. Right. Yes, I have pre-recorded exam review session for previous semester, so of course I can recycle it, but I added some other problems. So. All right, okay. So every time in order to get information about the flux, we need to analyze three parameters: B, magnetic field, A area, and the angle between them, right? So we're going to do it. So if flux is going down, then system becomes supportive, like Florence Nightingale. You remember I told you. In that case, induced magnetic field produced by induced current is in the same direction as the external magnetic field, which produces all this mass. Then if flux is increasing, system, the loop, doesn't like it. It doesn't like when flux changes, right? In this case, the system rebels. Right? So in this case, induced magnetic field will be in the opposite direction to the external magnetic field, right? And of course, then you can use right-hand rule number 2 in order to find correct direction of the current. So Faraday's law, we're going to practice it. Then after that, we moved into inductance, because all that stuff about Faraday's law and Lenz's rule is used in the inductance, right? In physics of the inductor. So we introduce inductance in general as the ratio flux divided by the current. Like if you have a, I even don't move this hand, trying to keep the wires kind of steady so that it wouldn't disturb the mic. So if you have, for example, like a solenoid, of course there is a magnetic field inside, of course there is a flux. and everything is produced by the current. So the total flux in the solenoid divided by the current which produced that flux. So that's what that's how we introduce inductance, L, right? Units of Henry, right? Units of flux, magnetic flux, Weber. Right? So then we applied that formula for a solenoid. We derived it, and again, you remember, it depends only on the geometry and the material inside of the inside of the solenoid, right? Mu naught n squared, n number of loops, a cross-sectional area, and okay, it's not I, it's L length. Okay, sorry, typo. Right, so length of the solenoid, length of the solenoid. Right. Okay. So then after that, we looked at the potential difference, right, across the solenoid. Because what is basically a solenoid? It's a bunch of loops, and exposed to the magnetic field, flux changes. Of course, there will be EMF in one loop, in the first loop, then in the second loop. Is the final accumulative? Okay, yeah, I should have mentioned that at the very beginning. So kind of accumulative. All right, but usually every time about 70% of the exam, final exam, is based on the new material, right? Okay, 65–70% of the new material. And then the rest is based on the old material, right? Something fundamental. Sort of kind of accumulative. But again, the thing is, we already tested you about the previous material. So how many problems total? I think the example, the final exam from fall 2019, I think, is in the Blackboard. So you can look at the example. But I can tell you, 5 multiple choice questions and 6 big problems. So overall, 7 problems. First, again, multiple choice questions, and then 6 big problems. Usually, I found that it's enough for students to make you busy for 3 hours. Let's put it this way. So overall, 7 problems. So, yeah, potential difference across the solenoid, delta V. And again, you need to remember which V is final and which V is initial. So if current enters here, so it's initial point. Current leaves here, it's a final point. So it's a V final minus V initial. That's what delta V. So it's a negative L inductance times rate of change of the current. Okay, so that's what we introduced. After that, we moved basically to optics slowly. We introduced Maxwell's equations and logically moved into optics. And before we moved into optics, we learn about traveling wave equation, because it's all about, after that, it's all about traveling wave equations. So traveling wave equations, equation, y, right, displacement of a media, right, equals amplitude of the wave times, it can be sine, can be cosine function, it's not a big deal, right? And then kx plus minus omega t plus phi naught, again, k. Completely new for most of you. K is a new parameter, new quantity. Wave number, we introduced it as 2 pi divided by wavelengths. Wavelengths, it's a spatial periodicity, right? K, it's a spatial frequency, basically. So all spatial information about the wave is in this first term, kx, right? Then all the temporal information is in the second term, omega t, right? Omega, we introduced it in this way, similar to the way we introduce wave number, 2 pi, but now divided by temporal periodicity, t, period, right? So here spatial periodicity, there temporal periodicity. And all right, so again, all temporal information is there. Then speed of the wave. All right, speed of the wave, it's neither temporal nor a spatial quantity. It's a mixture. It's a mix, right? So it's basically, it works as a bridge between spatial parameters and temporal parameters, right? So, and you see we have lambda f, or lambda divided by t. Lambda, it's a spatial parameter, t, temporal parameter. Or we can use it, we can find it as omega divided by k. Again, temporal parameter omega divided by spatial frequency k. Right. Then plus minus another place for many students for mistakes, right? So if you have plus, it means that this wave propagates in the positive x direction. Direction of wave propagation is in this variable. If you have here y, it means it propagates in the y direction. Wave propagates. If you have here z, it means that the wave propagates in the z direction. Very, very common place for many, many mistakes, right? A direction of propagation. So be careful, right? Don't just use x. Look, read the problem carefully, or look at the picture if the picture will be given, right? Direction of propagation. All right, so if plus here we have direction of propagation, in this case minus x. If you have minus, direction of wave propagation in the positive x direction. So again, common place for mistakes. So after that, we started applying that for electromagnetic waves. All right, so in this case, we have two traveling waves. Live together, propagate together, and you remember they live this happy life of sharing ups and downs, so they oscillates in unison, exactly, all the time, right? So when we have maximum electric field, maximum magnetic field, zeros again at the same place at the same moment of time, they live happy life. All right, so then, and all the time, these three directions are perpendicular to each other. Direction of the electric field, oscillations. Electric field oscillates this way, but wave propagates that way. Magnetic field the same, oscillates in this direction, but wave propagates perpendicularly. Perpendicular, because it's an example of a transverse wave. All right, so E perpendicular to B and perpendicular to the direction of wave propagation, direction of speed. Then, all right, so as I said, they oscillate in unison, right? So it means that this part of a traveling wave, this sign kx minus omega t plus initial phase, exactly the same for the electric field and magnetic field of the electromagnetic wave. So this part exactly the same. The only difference is in the amplitude. Right, amplitude of the electric field and amplitude of the magnetic field. Amplitude of the electric field is way, way, way larger. It's larger by a factor of c, speed of light. My neighbors are doing some construction, I don't know. All right, so E naught equals c times b sub 0, right? So then, yeah, in this case, so electromagnetic wave propagates in the x direction, electric field oscillates in the y direction, so that's why we have a subscript here, E sub y. This subscript tells us in which direction electric field oscillates, right? And then B. B oscillates in the z direction. Wow, it's the first time in almost a year they're hitting something. So then magnetic field oscillates in the z direction. So as a result here, subscript z. Again, these subscripts and that direction of propagation, that's the 2 points where most of students make mistakes on the exam if I give a problem about electromagnetic waves. So be careful. Direction of wave propagation and directions of oscillations, different things, right? So you have to read problem carefully and look at the diagram. So then after that, we started discussing interference. So if you have two traveling waves, identical traveling waves, right? So the same amplitude, the same frequency, the same period. No, the same, better to say the same period and the same wavelength. Yeah, spatial parameter and temporal parameter. All right, so in that case, yeah, it's possible that at some spots we're going to have constructive interference, when the amplitude of the resultant wave is doubled, and points where amplitude will be 0, right? Those two waves, they just completely cancel each other, right? As a result, displacement of the medium will be 0. So, and we derive this condition. So, yeah, also you remember that there's this construction in the parentheses. It's called the phase of the wave. So this is phase of this wave. This is phase of that wave. So, and that's what we have here, delta phi, right? phase difference between these two waves. So, and we derived, so if 2 pi over lambda times the path length difference, delta r path length difference, plus the inherent phase difference, delta phi naught. Delta phi naught is just a difference in the initial phases of the first wave and the second wave. Inherent phase difference, so if this construction equals to integer number of 2 pi's, right, so we're going to have constructive interference. If it is equal to m plus 1 over 2 times 2 pi, then it's at that point there will be destructive interference. So great. So now after that, we moved into interference of light, right? And we looked at double slit experiment. Right? So when you have two slits, laser light hits it. Oh, we illuminate it with the laser, right? It must be, the source must be monochromatic. And then as a result, on the screen, we can observe what is called interference fringes, right? And of course, we can define their positions either using angle, but measuring angle is not very convenient, so we switched to measuring a distance from the center of the screen to the current, to the point where this or that bright spot is, right? So that distance ym equals m lambda L. L, it's a distance from the screen, from the double slit to the screen, this L distance, right? And divided by D. D, it's a distance between slits, D. Right? So that then in a diffraction grating, basically it's a improved double slit system. So we improved it naturally, and as a result, we ended up with the diffraction grating where we have thousands of slits, right? And the distance between them is on the order of microns, a few microns, right? And then if you illuminate the diffraction grating with the laser light, then on the screen you're going to see improved interference pattern. So at the center, again, you're going to have a bright spot, which corresponds to integer m equals 0. Then this corresponds to integer number 1. This is 1, then 2 and 2. And in order to describe positions of those bright spots, we have to use these two formulas, right? Okay, let me frame it. So the first formula, d sine theta equals m lambda, give us a position of these bright spots in terms of an angle, right? So this, for example, theta 1, that will be angle theta 2. So this allows us to find angles. But if you don't want to deal with angles, and if you want to measure distances, of course, you have to use the second formula. So ym equals L times tangent of the corresponding angle. Right? So that's what we introduced discussing diffraction grating. And now the last part, which we discussed only in the lecture, ray optics. About ray optics, a few words. Right. So now, ray optics. So we only discussed what? Reflection, law of reflection, and Snell's law. So if you, let's say, you have a boundary between two media with index of refraction, what the first one, let's say, n1, the second is n2. And let's assume that we have a ray hitting this surface, right? Or incident on the boundary. So this ray is called, of course, incident ray. So then there will be reflected ray, right? And we use these angles to define directions of these rays. Careful, again, it's another place for some unnecessary mistakes. So we use the angle between the normal line and the ray. So that's the angle we use. So this is theta sub I, angle of incidence. And this is, of course, angle of reflection, theta sub r. And according to the law of reflection, these two angles are equal to each other. Right? So first, theta I equals to theta r. Basically, part of the law of reflection. But at the same time, if the second medium is transparent, of course, some light will be able to get into the second medium. Right? And again, that ray, direction of that ray, can be defined by using this angle, again, between the normal line and the ray. So this is theta, which way I label it? Okay, let me call it just theta 2. It's an angle of which defines position of the refracted ray, angle of refraction. Right? So this, you know what? Let me use theta 1, right? So, okay, like incidence, right? So let me call, let me denote theta I as theta 1, because now in order to write Snell's law, I need to switch to subscripts 1 and 2. So let me just, instead of theta I, let's use theta 1. And now I can write Snell's law eventually, in the form which you can find in any book. Right? So Snell's law, as a result, then you can write Snell's law. So N1 times sine of theta 1, 1 and 1 subscript, equals to N2 times sine of theta 2. N2 times sine of theta 2. Right. So, Snell's law. Most of you are familiar with this law. Right. And yeah, I started using index of refraction, but let's just introduce it as well. Right. So, index of refraction, N, is defined as the ratio of the speed of light in the vacuum divided by the speed of light in the medium of the medium, and that index of refraction is the index of refraction of that medium. Right. Okay, so enough of this review. Now let me restart the camera, and we can start looking at examples, problems. So the first problem is about magnetic force. So that first section. So let's assume that we have this wire. Okay, let me put a bullet, first bullet, and let's say we have this wire with a current. Current goes this way. So I. And so there are a few charges. Let's say this is, here there will be positive charge, let's say plus. Here there will be another charge. Yeah, let me position it here. All right, and then two negative charges. So we will discuss directions of forces acting on these charges. All right, and one by one. So in order to find the magnetic force acting on them, of course, first we need to find the direction of the magnetic field. Direction of the magnetic field is a piece of cake. Right-hand rule number 2. You remember, outstretch your thumb in the direction of the current and curl your fingers. So above magnetic field will be dots, below crosses. Right? So above magnetic field will be represented or can be represented by dots. And below, of course, crosses. Right? So these are magnetic field. Right. Okay, so now QVB. So let's practice right-hand rule. Direction of the force. Again, 2 steps. First, direction of cross product VB, and then quickly check what is the sign of your charge. if charge is positive, that direction is the direction of the force. If charge is negative, flip that direction in order to find direction of the magnetic force. Careful, right? Although very often, okay, not very often, sometimes students even remembering that they still forget about flipping direction. I've seen it in the past. So, okay, probably I should write the formula, of course, which we are planning to use. All right, so V cross B. All right. So let's start with the first one. And which piece of information I forgot to give you? Without that piece of information, we wouldn't be able to move any further. What if this charge is stationary? What if this charge doesn't move? Then, of course, magnetic force will be zero. You remember, in the magnetic world, everything is in dynamics. In order to produce magnetic field, charges must move. In order to experience magnetic force from the magnetic field, a charge must move again. So everything is about dynamics. Velocities are everywhere, which makes life more difficult in the world of magnetism. Right? So I didn't show the velocity, directions of the velocities. Right? So the first one, let's assume it moves to the right. So let's assume it moves this way. So this is direction of the velocity. Without this, nothing can be done. So direction of velocity we know, B also. So let's see. V that way, right? Then B is out of the board, so I have to position my hand like this, so along V. And now I can curl my fingers in the direction of the B, which is the second vector in the cross product, so V cross B. So I'm getting the direction of the cross product is down. Plus charge is positive, so that is the direction for the magnetic force, right? So I'm getting right direction, yes, exactly. So direction of the force is down. So that's the magnetic force acting on this charge. Right. So now, next, let's play with this. For example, again, direction of the velocity is needed. So which direction I have in my notes? Let's move it this way. Oops. So that's the direction of the velocity. So the same, V cross B. First, align your hand in the direction of the first vector in the cross product, V, which in this case is up, right? Then a magnetic field is it's into the board. So I have to position my hand like this, right? So now V cross B, you see, I'm curling my fingers in the direction of B, V cross B. As a result, my thumb gives me direction of the cross product. Then, since charge is positive, so this direction gives me a direction of the force. So direction of the force is this way, F, right? Okay, let me check if I'm getting the same. Yeah. Now, okay, let's do this. So again, direction of the velocity, which direction? Let's move it up. V. Again, V cross B. V is up, B dot dot is out. So I have to position my hand like this, right? So V cross B, and my thumb gives me direction of the cross product. But check the sign of the charge. Charge is negative. So that direction must be flipped to this direction. So the magnetic force is to the left. Again, cross product that way, but because charge is negative, so the force must be this way. So this is direction of the force, F. Okay, my neighbors tonight are loud. Sometimes they do it. All right, so next, what's the direction of the velocity? Let's send it to the left. So let's say this is direction of V. So again, V cross B, V that way, right? Then B cross, it's into the board. So I have to position my hand like this, right? So V, then cross B. So I need to curl my fingers in the direction of B. And so the cross product V cross B is down. But again, charge is negative. So we need to adjust the direction by flipping to the opposite one. So force will be up. force is up, right? Yeah. So it should be enough, right? About that formula, of course, then you can find absolute value. It's not a big deal. Maybe I can write, so the absolute value, of course, it's a QVB times sine of angle between them, right? So it depends on the problem. You shouldn't have issues finding absolute value. Enough of that formula. Now, next one. Let's play with this. That will be a reasonably big problem, so I need to probably erase it all, and yeah, I want the whole board. Cool. Okay, right, so let me erase this, and now this will be the first big problem. So let me put 1. So what's the situation in this problem? All right, so let's assume that we have a rod, a piece of wire, and through which we can send a current. So it is also attached to 2 springs. Spring over here attached to the wall. Let's say here there is a wall, and here there is a spring 1 and spring 2, identical springs. And if the whole system is exposed to magnetic field, right? So the first situation, again, initial situation, 2 springs exposed to the magnetic field. This is the conducting piece of wire, conductor. And when there is no current in the wire is over here at this point, right? Then, so basically this is an equilibrium. Forget about the force of gravity. There is no gravity, right? Then let's assume that what if you turn the current? So now let's assume that current flows through this wire. When the current flows, this wire will be displaced towards me by a certain distance, which is given. Of course, the springs will be compressed, right? And so this will be new equilibrium. So when current was off, the wire was here. When you turn on the current and current was flowing downward, wire moved up here. So now it's a new equilibrium position. Right? So we need to find direction. We need to find the value of this current. Right? So basically, this device can be used actually, for example, to measure the current. If you calibrate it properly, right? So let's say this point is 1 amp here, 2 amps, 3 amps, and so on. So by looking how far wire gets displaced, you can say the value of the current, right? Yeah, some kind of amp meter. So now let me draw the picture. I probably need to start with a wall. So let's say this is the wall. Then I will draw the picture when the rod is displaced already. So when current is flowing. So let's say here's the first spring compressed. Here's the second spring already compressed. And this is our piece of wire with a current. And we only know the direction of the current. So let's this is direction of the current. And as I said, that's what we need to find. Then, of course, as I said, yeah, let's write. So springs are identical, so spring constants are given, right? And then the whole thing is exposed to an external magnetic field. Direction is out, dots. So let's say this is direction of the magnetic field. All right, so let's say this is B. And, okay, let me start writing numbers. So K is 10 newtons per meters. Magnetic field direction is given, absolute value, 0.5 Tesla. Then the length of this rod, which is exposed to the magnetic field, is also given, and that number 20 centimeters. Okay, so let me show you this. All right, so L. So L is 20 centimeters. So what else is given? Displacement of this wire. So again, when the current was off, the wire was here. Right. Probably let me use dash line because solid line kind of doesn't look. Okay. So let me show that this is position of I, okay, not of the wire. Let me write of the wire. Of the wire when current was 0. As a result, now I can show in the picture the compression of the spring and displacement of the rod. So this distance is, which way I label it? Delta x, yeah. Delta x, and that delta x is 1 centimeter. Right. Delta x is 1 centimeter. Right. Okay, so let me check if I gave you everything. It looks like, yeah. Yep. So now we need to find current, as I said. Find I current. So let me introduce also coordinate system. All right. The origin will be at this point where the wire was when there was no current in the wire. So let me introduce this x, and this will be x equals to 0. X equals 0. Yeah, and probably I should write also no gravity. Forget about the gravity. No gravity. So, yeah, that's it. And so now let's discuss what do we have to do to solve it. From fundamental point of view, let's start. Which equation do we have to use in order to describe, for example, position of this rod over here? It's effectively kind of physics 2 problem, but at the same time over here there are tons of physics 1 ideas. This type of problems we discussed at the end of the physics 1 course. It's called static equilibrium. Static equilibrium. You remember which equation we used to discuss static equilibrium problems? Most of the time students don't remember, except for a few students, right? In order to get to the right equation, and actually we used this semester, we used that already, and I already discussed similar problems. So look, any motion of any system, classical system in the universe can be described by a law. Which law? And most of you most of you know that. Actually, everyone in the world knows that law, right? Because it's the most popular law. Newton's second law. F equals ma, right? So basically, but effectively, it's just an equation which allows us to describe motion of any system. In our case, yeah, we have a system, but do we have motion when it's already displaced now? Static equilibrium, new static equilibrium. There is no motion. Acceleration is 0, right? So Newton's second law applied, Newton's second law applied over here. We can apply it over here, of course, assuming or using the fact that acceleration equals 0, because it's in this case, system doesn't move, right? Okay, so now let me write. Maybe I will separate it. So from Newton's second law. So sum of the forces. Okay, we have one-dimensional system, so let me drop vector signs. I'm not going to use vectors. We're going to just use plus and minuses. Again, you remember positive vector in the positive x direction. If a vector is negative, it means it points in the negative x direction. So equals to ma. So this law describes motion of any classical system. But in our case, we have no motion, and no motion, it's a special case of a motion. Right? So in our case, acceleration equals 0, no motion. Right? So as a result, we can dump this acceleration. As a result, we're getting the equation which we have to satisfy. And using this equation, we should be able to find what needs to be found. So that's the beginning. Net forces. Yeah, not net force, right? Net force acting on the wire must be equal to 0. So now you see what we need. Now we need to draw all the forces, all right, and then balance them. Okay, so now you see what needs to be done as a next step. So 2 springs, they are compressed. Right? So of course they're going to exert forces, spring forces, in which direction? That way. Because for those springs, this is equilibrium position for the rod. Right? So of course they're going to exert forces that way to our right. So this will experience the force F spring, and of course exactly the same from the second spring. So we're going to have 2 identical forces, right? Then what else? There must be some force acting to the right, or to the left. Why? Because that force displaced actually the wire from that equilibrium position to this equilibrium position. And of course, obviously, that force is a magnetic force, because we have, when we turn the current on, current flows, exposed to the magnetic field, of course, there must be magnetic force pointing to the left. And actually, we can check it easily, right? So, direction of that force. Direction of L, it's the direction of the current. Current, we know, flows downward. So, cross product of L cross B, B is out. B is out. So L is down, B is out. So I have to position my hand like this, right? So sometimes you have to move yourself in order to make to find the cross product. So again, L is downward. This L direction of the current, and then cross it with B. B is out, so I have to position my hand like this, right? And my thumb gives me direction of the force. Yeah, it's to the left, where we expected to see that force. Right, so this will be Fm, magnetic force, right? That's it. There is no gravity, right? Or maybe we can, for example, position the whole system on a horizontal frictionless surface, right? In that case, force of gravity will be just balanced by the normal force. In that case, I wouldn't have to write no gravity. But anyway, let's assume that there's no gravity. Right, so these 3 forces, they must balance each other. And from this equation, we should be able to find what is unknown current. Okay, so now, and now you see the reason why I introduced coordinate system. Because I need to know which forces are positive and which forces are negative. So spring force are positive. Magnetic force, negative. So it will be F spring plus F spring minus F magnetic equals to 0. So we're balancing these 3 forces. So now we just need to write explicitly all of these forces. Okay, let me write underneath. So F spring, of course, all right. You remember the value of the force, K times delta X. Now it's just an absolute value. It's just an absolute value. Because now we already know the direction of the force, so I'm going to just use K times delta X. So K times delta X. And then the magnetic force, again, we know its direction. We already showed the minus. So now let's just write absolute value. You know what, maybe over here I will write. So magnetic force, of course, formula in general, FL cross B, right? And now we just need to apply for our case, and again, absolute value, direction we already discussed, right? We already applied cross product. So absolute value, I, L, B, and sine of angle between L, which is direction of the current and direction of the magnetic field. Look, current straight down, magnetic field straight out. What's the angle? So current down, magnetic field is out, so 90 degrees, right? So 90 degrees between them. So sine of 90 degrees. So it will be I, L, and B. Okay, that's it. So now we need to plug it into the previous. So we will get K delta X plus K delta X minus I, L times B, and it must be equal to 0. So look, of course, this will be 2K delta X. K is given, delta X is given, L given, right? And B is also given, so we have only one unknown current in this equation. So balancing forces, we can find the unknown value. So this is the only unknown value. So, of course, we can solve it. For I, okay, so let me do it step by step. 2K times delta X equals to ILB. So solve it for I. I will be equal to K delta X divided by B and times the length of the rod, which is exposed to the magnetic field. So that's the expression, right? And now if you plug numbers, again, don't forget to convert to meters, right? So you will end up, okay, maybe I will plug numbers, right? So 2 times 10 newtons per meters times delta X. 1 centimeter, it's a 10 to the power of minus 2, right? Or 0.01 meters, and divided by B, 0.5. Oh, magnetic field is kind of strong, 0.5 Tesla is a strong field. L, 20 centimeters, 0.2 meters. Okay. So let me write the answer. So the answer will be 2 amps. So that's the problem. Okay, not ridiculously difficult, but at the same time, not ridiculously simple. Sort of in the middle. And again, it's 50% of this problem, it's a physics 1, and 50% of this problem, physics 2, actually. It's a nice mix of both subjects. Okay, let me stand for a second here. All right, so this problem you can read by yourself. Okay, and I will send you my notes. It's a similar, again, about the magnetic force acting on the wire. This about cyclotron motion, also we'll skip. Okay, enough about magnetic forces. Now let's discuss Faraday's law conceptually, and then one problem in details. So now a couple of conceptual questions. So first about this. So let's assume that we have different okay, oscillating systems. Okay, so the first one is, let's say, let me make it bigger. So this loop, it's a loop, conducting loop, suspended from the ceiling. And the whole thing is exposed to uniform magnetic field which points out of the board, so B. Okay, I will draw several mics, several loops. It looks now like the mic is the major topic of the exam review session. Right, so let's say this is magnetic field uniform. And so let's assume that this loop, again I want to say mic, this loop oscillates back and forth, right? Sort of like a pendulum. Are we going to produce are we going to see an induced current in this loop. Right. So the question is, so what about EMF and, of course, I induced? Are we going to see any induced current in this loop? So in order to get information about the induced current, of course, we need to analyze what? Flux, right? Magnetic flux through the loop. Right? If that flux changes in time, then of course there will be induced EMF and induced current. So let's see, what about flux? So flux, again, as usual, it's a B dot A, 3 parameters, B, A, and the angle between them. In our case, what about magnetic field? As this loop oscillates, it stays within magnetic field all the time, and that magnetic field doesn't change in time. So it means that magnetic field is constant. So magnetic field doesn't change. Then area of the loop, also we just oscillate it without changing its area, right? So area stays the same. And angle, of course, I can pick the area vector, for example, out. So the area vector will be in the direction of the magnetic field. In the direction of the magnetic field, as a result, that angle is constant. So all 3 parameters constant. So flux is constant. So as a result, EMF is 0, and of course, induced current is 0. So in this case, nothing happens. It will just oscillate as a simple pendulum. Right? Now, second situation. Right. So now, what if we oscillate it in this way? So let's say we have here spring and the, okay, let me remove this, and the loop. So now the loop oscillates up and down. The same question, are we going to see any induced current? And the answer is the same. Again, we assume that this magnetic field is uniform and it goes to that infinity, right? So no troubles, right? Maybe I can add, so dot, 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 for example. Right. So now, again, 3 parameters, B, A, and the angle between those 2 vectors, B and A. B stays the same as loop oscillates, right? Then, again, area of the loop stays the same. And the angle also constant. Again, you can pick area vector, for example, out. So the angle will be 0 and constant. So in this case also, okay, let me separate this. So I induced will be also 0 for this system. Right? And now the last. So what if we have this system? So the loop. But now, what if this loop is spinning? Okay, with some angular velocity omega. So in this case, okay, let me write all parameters. So B still stays constant. We don't change the value of the magnetic field. Then, area of the loop stays constant still. We don't change the area of the loop. But what about the angle? So first, when the loop is in this position, area vector can be, where's my loop? Again, let me get the loop here. So first loop in this position, so the area vector is out. Then when we start turning it, right, area vector changes its direction. So angle first increases. Okay, not first, all the time. Increases, right? So as we spin the loop, this angle changes in time. And as a result, flux changes in time. And as a result, EMF is produced and induced current will be in this loop. So the angle changes. Right. So as a result, flux also changes. So as a result, induced current will flow in this loop. So I induced, of course, is not 0. There will be induced EMF and induced current in the loop. Okay, this is something which can be on the among multiple choice questions. So now another situation. I think something similar we discussed in our lecture. So what if we have current, right, flows this way, right? And this current is constant. Current is constant. And now we have a loop. Let's say the loop is this. And it's being moved that way, velocity. Right? So are we going to see any induced current? So the question is about induced current. I induced. The same thing, we have a magnetic field produced by the current. So let's find quickly direction of that magnetic field. So my right-hand rule number 2, I would stretch your thumb in the direction of the current, and then magnetic field on this side will be out of the board dots. Right, so this will be dot, 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 and of course on this side, opposite cross, cross, and cross. So these are our magnetic field lines. Okay, so what happens to the magnetic field as we drag this loop in that direction? So magnetic field in time doesn't change. Of course, magnetic field in space changes, right? So of course, magnetic field over here will be stronger than here or there, right? But those are changes in space. We don't care about magnetic field or any other parameter changes in space, because what we care about changes in time, d phi over dt. So as you move this loop along the wire, magnetic field in time doesn't change. So it stays the same, right? So magnetic field constant, area of the loop again stays constant, and angle again, I can pick area vector out in the direction of the magnetic field, so the angle will be 0, and again constant. All three parameters constant, so flux is constant, and induced current will be 0 because induced EMF will be also 0. So induced current is 0 because flux is constant. Flux is constant, and as a result, induced current is not produced. So now, next loop. What if we take similar loop, but now drag it in that direction? Right? Again, we need to find out what happens to the flux and see if that flux changes in time, only in time. So as we move our loop that way, magnetic field now, as you move, magnetic field through the loop becomes weaker and weaker and weaker. It changes, of course, in space and now in time. And yeah, as we move, magnetic field becomes weaker in time. So it means that flux is also going down, right? It changes. Area of the loop stays the same. Area constant. Angle will be also constant. I can pick the direction of area vector into the board, so angle will be 0. So area stays the same in this case. Angle also stays the same, but magnetic field in this case is going down, again going down in time, with time. So in this case, of course, flux is, maybe you know what, we can find even the direction of the induced current. So let me do it. I will probably do it here. So B is going down, area vector stays constant, area, then angle also constant. So of course, flux is going down. System, which is the loop, doesn't like when flux changes. You remember, of course, in this case, since it's dying, of course, the system becomes supportive. So it will drive the current in such a direction so that the induced magnetic field will be in the same direction as the original external magnetic field. Right? So the first option. So in this case, all right, so I can write, so B induced is in the same direction as B external. So I can draw within loop a few induced magnetic field lines. So cross, cross, cross. So these are B induced, right? And now after this right-hand rule again, number 2, in order to match these directions, crosses into the board. So I have to position my hand. Okay, again, where's my loop here? So loop, induced magnetic field is into the board. So I have to position my hand like this in order to match that direction, right? So as a result, my thumb gives me this direction, which is clockwise. Right. Let me check if I'm getting, yeah, correct direction. So then this will be direction of I induced. Right. So now I induced in a clockwise direction, and we use right-hand rule number 2 to find that direction of the induced current. So now, so we discuss here conceptually Faraday's law, figuring out if there is an induced current or not. And now let's look at the problem. Right. So I will have to erase this. Okay, for only the first part. So this is actually the second big problem, right? So second big problem. So let's assume that we have a square conducting, made out of conducting material. Right, so let me draw it. And there is a resistor. Right. So resistance 10 ohm. I hope you don't hear. You're not hearing conversations of my friends, of my neighbors, not friends. Tonight they're kind of loud. Okay, then geometry. Geometry, it's a square actually. It's a square. So it means that this is, let's say, this is 20 centimeters A, 20 centimeters, and this is B also 20 centimeters. Then the whole thing is exposed to an external magnetic field which points into the board. So let me draw a bunch of crosses. So that's B. External, maybe let me emphasize. So then what else? Resistance, yeah, I wrote. Right. Then, so there is a current. No, the magnetic field changes in time. Okay, so this external magnetic field changes in time. So let me write, so B external. Okay, maybe I will write changes. Let me write changes linearly, because it's a very important piece of information, linearly. Linearly in time. So first, B initial. B initial equals to what? 0.5 Tesla. 0.5 Tesla. And then it goes to B final, which is 0.5 Tesla. And this transition happens in the period of time 63 milliseconds. So we have a conducting loop. There is a resistance in that conducting loop, right? Exposed to the magnetic field, and that magnetic field changes in time with this rate. And again, changes linearly, right? So what we need to find? We need to find the average induced current, right? And its direction, right? Is it flowing from point, okay, we can say this point, let's say this point A, and this point B. Is it flowing from A to B or from B to A? So that's how our problem is stated, right? So it's direct applications of Faraday's law. Right, so we have a loop exposed to the magnetic field. Something happens to the magnetic field, but anyway, there is a magnetic flux. Magnetic flux, again, somehow changes in time. We will see how. And as a result, if flux changes in time, of course, EMF will be produced. So we can calculate that EMF, and then we should be able to find the induced current because resistance of the loop is given, right? So we've done similar problems, but we are reviewing everything, right? Right, so let's start with direction. And again, we're going to apply Faraday's law in 2 steps. First, I will apply Lenz's rule to find a direction of the current, induced current. And then, of course, we will apply Faraday's law to find the value of EMF and the value of current. So let's first find direction. So similar train of thoughts I will write. So 3 parameters, B, A, theta. You know what? It's time to erase this. Yeah. So area of the loop. We don't change the shape of the loop, right? We don't distort it. So area of the loop is constant. Then angle. I can pick area vector in the same direction as the direction of the external magnetic field, so A. As a result, in this case, the angle is 0 because direction of B in direction of A into the board. So it's 0 degrees, and anyway, it's constant. Magnetic field, explicit information, magnetic field is going down. Right. So as a result, if we combine them all, because the flux, it's a B, A, and cosine of angle, so we can come up with a conclusion about the magnetic flux. So magnetic flux is going down. So magnetic flux is dying. So the system doesn't like it. System wants to keep flux as constant as possible. So in this case, the system becomes supportive, like Florence Nightingale, right? Helping. So it means that B induced will be in the same direction as B external, right? And so within the loop, I can draw a few crosses, so many crosses of different color, right? External magnetic field, area vector, and now induced magnetic field. So let me show that these are B induced, right? So, and now right-hand rule number 2. So now instead of a circular loop, we have a rectangular loop, but who cares? Our rule is the same. So induced magnetic field cross, it's into the board, right? So I have to match it by positioning my hand like this, right? So in this case, my fingers is into the board also like these red crosses. If I position like this, direction will be different, right? So as a result, I'm getting clockwise direction of the induced current. So as a result, I induced CW, right? Let me check if I got, yeah, CW direction. And so now we can tell in terms of if current flows from A to B or from B to A. So current clockwise this way, so I induced, and through the resistor So through a resistor, that way clockwise. So it means that from B to A, right, clockwise. And we can write, we can actually answer the question which problem says, or asks. So from B to A. So it's the first part. That was the first bullet. Now the second bullet. Let's find actually the value of EMF, right? So EMF equals, and now we know the direction, so we're going to use just the absolute value of that expression. All right, so magnetic flux. Of course, it's just a B dot A, right? And we just discussed already a direction of A, so the angle is 0, cosine of 0 degrees is 1, so this can be written just as BA. Right. So we can plug it here, minus I can drop now, so it will be d over dt of BA. Okay, absolute value. So carefully, which quantity is constant? B changes. It's not constant in time. Area constant. So we can take this A and extract it from the sign of differentiation. And of course, area, again, it's an absolute value of the area vector. It's also positive, so we can extract it out of the sign of absolute value. Right. So I can write it as A times dB over dt. And now it's time to use this word, that magnetic field changes linearly, because now, yeah, it's time to recall. If it changes linearly, it means that I can replace this dB over dt with delta B over delta t. So let me write, since B changes linearly, so I can write dB over dt as delta B over delta t. Because what is effectively dB over dt? It's a slope of the curve. If you plot B versus time, look, if I plot it here, for example, let's say B versus time. So let's say this is initial moment of time, t initial, this is t final. And over that stretch of time, magnetic field changes linearly. Right? So first it was constant, then it went down, and then it stayed constant again. So this is B initial, and this is B final. So this dB over dt is just the slope of this part of the graph. And since it changes linearly, it's a straight line. So it doesn't matter if you calculate the slope using infinitesimally small dt or finite delta t, the slope will be the same. Right? So we can write it as A times absolute value of delta B over delta t. All right. Okay, so now basically everything is known. So area A by B, A, B, and so delta, okay, let me write, so first in terms of a symbol, so it's a, and again, don't forget which value final, which value is initial. Actually, in this case, anyway, we're looking at the absolute value, so you're not going to make a mistake. But anyway, let's follow the rules. So B final minus B initial, that's what delta B is. Delta every time final value of something minus initial value of something. So it's B final minus B initial and divided by delta t. Right? Okay, so let me write numbers. So 0.2 meters times, times 0.2 meters and times, all right, 0.5 Tesla minus 1.5 Tesla divided by 63 milliseconds. 63 times 10 to the power of minus 3 seconds. right? Of course, I'm not going to calculate. I'm going to look at my notes. 0.6349. We found EMF volts. I use more sig figs because it's not the final answer. Right. It's better to keep a few extra. And so the final, this is EMF, but what we need to find induced current. So induced current, of course, can be easily found using Ohm's law. I induced equals to EMF divided by resistance. Resistance is over there. So if you plug it, you will get 63 milliamps. Huh. Okay. I'm just surprised. You know why I'm paused for a second. It's just the time, 63 milliseconds, and now we found current 63 milliamps. It's a nice coincidence, right? That's why I paused for a second. Right? So this problem next, again, about Faraday's law, it's a very, very similar to the problem which we discussed in the class. And you had in your homework, right, loop being dragged out of the magnetic field or into the magnetic field, right? So you can refresh it by yourself. Okay, so now, next, enough about Faraday's law. Now let's discuss, let's look at one problem about inductance. So I need to erase that. Okay, yeah, we'll start erasing. This one is reasonably simple, but we just need to discuss the major points of how to treat the inductor and find the potential differences across an inductor. So this will be problem number 3 as far as I remember, right? So now inductance. Or maybe I will write, so inductance. Okay, this is my fancy just I, right? I. It's not Y, it's I. Right. I know students are laughing sometimes at that, but that's how I write I. So we have a solenoid, basically an inductor. Inductance is given. Right, so L equals what? 280 millihenry. Units of inductance, Henry. Units of magnetic flux, Weber. Right. Then, you know what? Let me draw it. Let me draw a solenoid. So let's say we have this. This is the solenoid. And of course, it can be a part of a complicated circuit, right? But for a discussion, I just want to see a battery which produces current or drives current through the solenoid. But of course, yeah, it cannot be. It's not a real circuit, right? Never try to connect an inductor directly to a battery. It's very, very, okay. In a nice words, it's a silly idea. Right, so, right, okay, something like this. And of course, as I said, this battery is going to drive original current. So which probably I use blue. So this drives, let's call it I0, original current. And yeah, inductance, L. So then what happens to the current? This I0 changes linearly, and it's going down. Probably I will write, yeah, I0, again, changes linearly. So I0 initial is 25 amps, and final value of the of this current I naught is 10 amps. And this all happens in the period of time 360 milliseconds. Delta T, 360 milliseconds. Okay, now I can erase the rest. And so what we need to find, the magnitude of the induced EMF. Right. So we need to find, effectively, okay, it's better to stay just, we need to find delta V across an inductor. And again, delta V delta every time, final value minus initial value of something. So again, which point is final, which point is initial for a solenoid. So it's important, let me emphasize. So where current exits the solenoid, that's the final point, and where this current I naught enters the solenoid, that's the initial point. And over here, I also emphasized on that. Final, initial. So, of course, we have a formula. We can just plug it, plug and play, right? But first, let's discuss conceptually. So which piece of physics is actually works inside of this inductor? It's a Faraday's law. It's a Faraday's law because, again, what is effectively a solenoid? It's a bunch of loops, 1, 2, 3, 4, and so on, thousands of loops, exposed to the magnetic field produced by this current. So, of course, if there is a magnetic field to the loop, of course, magnetic flux, and as we just discussed, of course, there will be EMF produced. But we have not just one loop. We have next one, here EMF 1, then EMF 2, EMF 3, 4, 5, 3, and so on, 1,000 of EMFs. And if you add them up, you're going to get this delta V, right? So a potential difference between the final point and the initial point, right? Okay, so that's, and of course, all that Lenz's rule can be applied, right? So what happens with the flux, right? So the system, the loop will respond, will start driving current in a certain direction. So strictly speaking, it's an application of all that stuff. But from a practical point of view, we adjusted those rules, right? Make them more practical for a solenoid, right? And now instead of using this Lenz's rule where the system tried to suppress or support flux, now we adjusted that Lenz's rule for a solenoid. And now, what does solenoid do? It fights if this current changes. Again, in the Lenz's rule, system doesn't like when flux changes. It wants to keep flux as steady, as constant as possible. Now, in the solenoid, it's all about current. The solenoid wants to see current as constant as possible. If current constant, then the solenoid does nothing, and it is not going to produce any potential difference across the solenoid, across itself. But if current increases, the solenoid, no, I don't like it. I want to suppress it, so it will behave like a rebel, right? Suppressing that growing flux. In which way? It will produce a corresponding potential difference, right? So that the induced current will flow in the opposite direction to the original current, suppressing growing original current. Then, if this original current is dying, again, the inductor, the solenoid, doesn't like it. So now current is dying, so it will try to support it to keep it as to keep it constant, right? So, in which way it is going to support? It will produce a corresponding proper potential difference across this solenoid, right? And so that the induced current will flow in the same direction as the original current. Right? And again, this potential difference, right, we're talking about this delta V, It's produced by the solenoid, right? Made in the solenoid, right? Made in China, made in US, made in solenoid, right? So it's not produced by this battery. No, inside of the solenoid, you remember it has some amount of energy stored in the form of the magnetic field, and that energy can be used to produce additional EMF and drive and that additional induced current. Right? So now, again, it's basically, again, Lenz's rule, but adopted, adjusted for a solenoid. Right? Okay, so now let's discuss our case using this rule. So now our original current, what does it do? 25, final 10. Current is going down. The solenoid is not going to like it. All right, as a result, the solenoid will produce a proper potential difference so that the induced current will flow in the same direction as the original current, right? So it will flow, oops, I want to use a different color. In this, everything is fine? Okay, I heard some noise. So in the same direction, it means that the induced current will flow this way. I induced, right? In the same direction as the original current. And in order to produce, just a second, guys. All right. Okay. Right. So you see now both of these currents flow in the same direction. So now, in order to produce this induced current, this solenoid, I usually, you remember, I usually introduce it like an effective small battery, right? So this solenoid must work effectively as a battery with this polarity. Here plus, here minus, right? With this polarity, the induced current will flow from plus to minus, right? So it means that at the final point over here, potential is higher than at the initial point. Again, the reason why I usually draw this small battery, because if I draw this plus and minus, plenty of students got confused. They know the current must flow from plus to minus. They see plus here, minus there, and as a result, they just drive this induced current from this point to that point, this direction, which is wrong. They're missing the very important point that this plus and minus is produced by this whole structure. But the whole solenoid produces here plus and minus, and then the induced current flows through the rest of the circuit. In order to avoid making this mistake, driving current in the wrong direction, I usually sort of like squeeze this distance between this plus and this minus into a small battery. That's the logic. That's why after a couple of years of teaching this, I realized that it makes sense to talk about effectively small battery, right? So that students will drive the induced current in the correct direction. Right? So now here plus, minus, so it means higher potential, lower potential over there, right? So again, delta V, it's a V final, which is at higher potential, minus V initial, which is at the low potential. So delta V must be positive, right? So this delta V must be positive. So we just discussed conceptually how to get the correct sign of the potential difference across the solenoid. So now let's calculate. Let's calculate, using the formula. And of course, we will get that automatically from the formula. But first, I wanted to discuss it conceptually. So, all right, delta V equals to minus L di over dt. And this is actually original current. This rate of change of the original current. Okay, now so I added sub-zero. Right. And now we need to use, again, this word, that current changes linearly. It means that di over dt can be replaced with delta I over delta t, like what we've done over here. I erased it, right? Over there, we replaced dB over dt with delta B over dt. Now we're going to do the same with the current, right? So I changes linearly. So I can write equals to minus L delta I over delta t. Okay, I can add subscript 0 again to clarify. All right, so basically we're almost done. So now just simple minus 0.28 Henry. I convert it immediately or get rid of millihenry. Milli. N times delta I. So I final minus I initial. So it's 10 amps minus 25 amps divided by delta T, which is 300 milliseconds. It's a 0.36 seconds. 0.36 seconds. Right. So negative value here minus there gives us plus. And number, let me look at the notes, plus 12 volts. Problems similar to this without numbers, a few times I gave among multiple choice question, right? So you can see what happens, for example, with, you see how a solenoid responds, you see potential difference across a solenoid, can be given. And the question can be, what happens with the original current? Right? Again, so you see what will be the direction of the induced current. So you see the response of the solenoid. You can deduce immediately direction of the induced current. If that direction is the same direction, if directions of both of currents the same, then it means that original current was dying. If directions of currents opposite, it means that original current was growing. Right, so that's the problem. The next one, something similar, but with additional part. Skip it. Now, electromagnetic wave. I will skip traveling waves because in electromagnetic wave, we have two traveling waves traveling together. Electric field traveling wave and magnetic field traveling wave. So all these results applicable in the electromagnetic wave. So let me look at one problem. Definitely there will be a problem about one of the waves, maybe just traveling wave in general, or electromagnetic wave, or maybe acoustic wave, who knows what. Okay, so let me erase this. All right. And first, originally, when I had that problem with mics in the middle of the semester, actually I bought first one mic, Sony's mic, and then I didn't like that. I bought Lavalier, and then I returned the first mic. Now, because I thought, okay, it's a new one, it should last for, I don't know, a couple of years, but it lasted only for a couple of months. Right. So I need more of them. So electromagnetic wave. So now it will be problem number 4. So EM wave, electromagnetic wave. So what is given? Frequency. Not if word frequency is just used, it's a F. F is given. So F is 60 hertz. Okay, it's a very low frequency, right? Basically, radio waves. Electromagnetic wave. Okay, let me write propagating. Okay, propagates. Okay, maybe I will write it propagates. Propagates in plus z direction. So in a plus z direction, then amplitude of the electric field is given. E naught. E sub 0, it's a 2 volts per meter. Then, yeah, that's it. And what we need to do, we need to write an expression, basically function, which describes electric field, this, and magnetic field. So we need to write something like this for the electric field and for the magnetic field, right? So we need to find E as a function of, okay, you know what? I cannot write now variables on which it will depend, because we need to discuss that. So let me just write E and B. Okay, I will just write functions of E and B. Right. Okay. But of course, it means just finding this. You know what? Let me draw first a picture. I like drawing pictures because it simplifies understanding, analysis, right? It helps sometimes. All right, so first of all, it propagates in a z direction. So let me align z-axis, okay, position z-axis horizontally. Right, so this will be z, and then x and y. So x will be this way, y will be that way. Why such a strange orientation? Because you remember we usually use a right-handed coordinate system. Right-handed. What does it mean, right-handed coordinate system? If you take a cross product of x and y, you're supposed to get z. Right? In order, x, y, and you get z. And look, right-hand rule, x cross y, and you're going to get z direction. Right? So right-handed coordinate system. So that's why I aligned this way. So. Also another piece of information which I missed, right? Yeah, now I realize. Electric field oscillates in x direction. Electric field, 2 volts, and let me write, oscillates in x direction. Okay, important piece of information. Without that piece of information, of course, I wouldn't be able to draw. That's why now I realize that something is missing. Right, okay, so now let's draw. Oscillates in the x direction, so electric field oscillates this way. But the wave propagates in the z direction, so it oscillates this way and propagates that way. So let's draw it. All right, so it will be, let's see. All right, so this is electric field. Traveling wave. Right. So that's E. Then, the wave propagates in the z direction. So that's the direction of V. And you remember these 3 directions: electric field, magnetic field, and direction of the wave. They are perpendicular to each other. So it means that there is only one direction for B to oscillate, y direction. So the magnetic field must oscillate in the y direction. Right, something like this. So this is B. Right, so that's the picture. Okay, so now after this, let's actually write that. So what we need? Obviously, we need K, and we need omega. Initial phase, when it's a question about electromagnetic wave, very often people are not interested in the initial phase. Usually, waves oscillates fast, right? So in most of the experiments, it's not that important. So we're going to assume that initial phase is 0, and that's how I drew it, right? You see, we have sine function starting at 0. This is basically snapshot graph. Snapshot graph, we can say it t equals 0. So let me write. I'm reading the question in the chat. So electric wave and magnetic wave oscillates vertically and horizontally despite what axis it points to. No, they must be perpendicular to each other, right? They must be perpendicular to each other, and then along which direction they oscillate, it depends on the statement of the problem. It can be that information can be given in the picture, for example. But in our case, it's given that electric field oscillates in the x direction. I position my x-axis vertically. Of course, there's no problem. There wouldn't be any problem if I turn the coordinate system not slightly, by 90 degrees. In that case, x will be horizontal and y would be vertical, right? But in that case, of course, positive x direction would be that way, and positive y direction would be upward. So vertically or horizontally, of course, it depends on your axis. Right? In this case, again, I could have turned my coordinate system, and electric field would oscillate horizontally, but that magnetic field would oscillate vertically, but it will be still along x direction and y direction. So it depends on how problem is stated. Okay, good. Where was? Yeah. So now we need to find parameters. So yeah, let's find k, and then I will discuss what I thought about discussing. So let me start with omega, temporal parameter. Okay, let me start with omega. So small bullet, and what is omega? First of all, omega, it's a temporal frequency, basically. Of course, name is angular frequency, but of course, it's a temporal parameter. And we have some temporal information. Frequency, 60 hertz. It's a temporal piece of information. So it means that we should be able to find omega like that, easily, right? So you remember the definition of omega? It's just a 2 pi divided by temporal periodicity period. It's over here, right? 2 pi divided by t. And of course, frequency and period related, they're reciprocal to each other, right? So it will be just 2 pi f. Okay, so as a result, finding omega, piece of cake. Let me look at the number. 377 radians per second. 377 radians per second. Then, what's next? Yeah, k. So now k. With k, first we can say, okay, we might be in trouble because we have information, we have only temporal information about the wave frequency, right? And this is a spatial parameter. It's a spatial frequency. So how can we get spatial information about the wave if spatial information is not given? We have the speed. Speed, you remember, works as a bridge between temporal quantity and spatial quantity, right? And in this case, it's an electromagnetic wave. So it means that it propagates with the speed of light. And again, guys, if problem is about acoustic waves, don't use speed of light. I've seen it in the past, right? So I saw it happens. It can happen. All right, so yeah, through the speed of light. So it will allow us to move from these temporal parameters to spatial parameters. Right? So let me emphasize. So V, which is C, equals 3 times 10 to the power of 8 meters per second. Right. So what can be used? We can use either lambda f, or we can use. Yeah, we can use, probably easier to use omega divided by k. So C equals omega divided by k. Right, C equals omega divided by k. So from here we can get that k equals to omega divided by c. So omega is here. Divided by 3 times 10 to the power of 8 meters per second. So the answer will be, okay, let me look at my notes, 1.26 times 10 to the power of minus 6. Yeah, it will be in meters. Meters to the power of minus 1. 1 over meters. So now we're all set. No, not all set. What else is still missing? So yeah, we can write electric field function because we know amplitude of the electric field is given. But amplitude of the magnetic field is not given, right? But again, you remember, E and B are related, again, only in the electromagnetic wave through the speed of light. So electric field is way, 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 way stronger in numbers. Right, so now D naught will be E sub 0 divided by C. E sub 0 is 2 volts per meter divided by 3 times 10 to the power of 8 meters per second. Okay, so let me look at my notes. What will be the answer? 6.67 times 10 to the power of minus 9 units of Tesla after Nikola Tesla. Okay, and now, yeah, we're all set. Now we can write down what problem asks us to write. So let me start with the electric field. So the final bullet, E, which now again, as I discussed it over here, be careful with the direction of propagation and directions along which electric and magnetic field oscillates. In this, it is in these subscripts and that spatial variable. So which subscript do we have to use? Electric field oscillates in the x direction. So here we must have subscript x. Then, okay, variables on which it depends I will write in a second. Okay, I will of course write E and then the second variable. So then amplitude 2 volts per meter times sine K. Where is my K? Oh, yeah, K. 1.26 times 10 to the power of minus 6. Okay, I will skip the units. Now, which variable we have to write here? Spatial variable. Wave propagates in a z direction. So here must be z. So be careful, read the problem, look at the picture. It depends on how the problem is stated, right? So wave propagates in a z direction. So here should be z. Then plus or minus. Since the problem says it propagates in the positive z direction, plus z. Of course, after that there must be a minus, right? So plus minus. Plus means propagates in the minus direction. Minus means propagates in the positive direction of that wave axis. In our case, z. So propagates in the positive z direction. Then minus omega. Where's my omega? 377. Again, units I will skip. And times 2. Initial phase, right? So I can say that initial phase equals 0, right? So yeah, let me emphasize that this is basically snapshot graph. Snapshot graph. And let's say at t equals to 0. Okay, and so now, yeah, of course, now I can fill out this gap because we just discussed it propagates in a z direction. Okay, again, typical place for mistakes. this subscript and this variable. In the electromagnetic wave, this must be perpendicular to each other. So now magnetic field B. Obviously, now we know that there must be z over here, right? A function of z and t. And now, which subscript we must put here? Magnetic field oscillates in the y direction. So there must be subscript y. And so amplitude of the magnetic field this 6.67 times 10 to the power of minus 9 Tesla times, okay, yeah, why not? And the rest is exactly the same as in the electric field. Because you remember, it's a happy couple, they oscillate in unison. They share ups and downs, right? Incomplete. Unison, so 1.26 times 10 to the power of minus 6z minus 3.77 times t. So the only differences in the amplitude and, of course, directions of oscillations. That's the only difference. Amplitude and directions of oscillations, these subscripts. And again, sometimes I even just see, I ask, so write expression for the magnetic field. And students just will write, instead of B sub y, they just write y. No, that's a mistake, right? So, it's a magnetic field in the y direction. You cannot just write y. Because we are science majors. We're not in the philosophy, right, department or literature. You feel like writing that way. So we have to be precise. So that's a problem about these traveling waves and electromagnetic waves. So now it's time to discuss interference. Right? One problem about interference. Okay, I need to start erasing this. If you don't mind. Okay, I see. No more questions. Again, guys, if you need to clarify something, okay, start saying it. Yeah. So this should be problem 5 if I started losing count. I think it's number 5. So interference now. Two out-of-phase radio antennas. Okay, probably I will write that. So we have two out-of-phase radio antennas. Generate frequencies, what, F equals 300 megahertz. Still not that high frequency. All right. Okay, and I need to draw the picture because we need the picture in order to understand what happens. So let's say this is my antenna number 1. So let's say antenna number 1, and here say antenna number 2. And the person with sort of like a detector antenna, receiver, right? Person with the receiver walks around, and let's say at this moment of time, that person is here with an antenna. Okay, maybe I will draw it. Okay, so here's the person, right, holding the receiver antenna. To detect the net field. And that person is at this distance. So distance from the first antenna is R1 equals 2 meters, and this R2 equals to what? 5 meters. I took this problem, I used to give this problem on a quiz when we were at school, right? 10 minutes, so the students are supposed to solve it very fast. And we can say, let's say, yeah, actually, the problem says out of phase, right? So it means immediately that the inherent phase difference is 0. So of course we'll have to wait. Pi inherent phase difference is pi, right? So I'm talking about this. Or I can write, for example, this. The initial phase of the first source is 0, and initial phase of the second source is pi out of phase. Basically, I can present that piece of information in this way, or I can write in the statement out of phase. So identical pieces of information. Okay, so at this point, constructive or destructive interference? We need to answer that question. Okay, nothing else but conditions. We just need to apply carefully conditions. That's it. So delta phi equals 2 pi over lambda times the path length difference plus the inherent phase difference. And if it's equal to m times 2 pi, that's constructive. If it equal to times 2, m plus 1/2 times 2 pi, then it's condition for destructive interference, right? Again, physics, it's a simple, right? So this wave generates, right, waves, a wave, and these are wave fronts. You remember wave fronts, collections of crests. And this antenna generates its own wave, and these are wave fronts. So they interfere, right? Of course, yeah, where wave fronts overlap, those are points for constructive interference. Right? But of course, we're not going to, we cannot use that approach. We just need to apply this condition and see, because we don't know are we going to have crest or trough at that point from this or that wave. So it's better just carefully apply this. So delta phi naught, as I said, delta phi naught, it's a, by definition, it's a phi 20 minus phi 10 equals to pi out of phase, and we'll underline and show that we can get from that, from those words. And so now we just need to find delta R. Delta R, obviously, R2 minus R1. It's similar to the problem which we solved in the recitation class, but now I gave R1 and R2 because, yeah, I prepared that for the quiz, so I didn't want students struggle with geometry or spend time on geometry. So it will be, of course, 5 minus 2. It will be 3 meters. The path length difference is 2 meters. So basically, it's an additional distance that the second wave has to cover on the way to the receiver. Right. Okay, so now we can. No, wavelengths. Wavelengths. We need to find wavelength because it's not given. The frequency is given. But again, since this is the radio waves, part of electromagnetic spectrum. So it has a speed of, it propagates with the speed of light. Propagates with the speed of light. So now, so this is the first bullet. Second, it's about this, and now about the wavelength. So wavelengths, of course, it will be C divided by F. Right? So it's this. Right. Lambda equals V, which is C divided by F. Right. Of course, 3 times 10 to the power of 8 meters per second divided by 300 times 10 to the power of 6 or 1 over second hertz. All right, so exactly 3 times 10 to the power of 8. So the wavelength is 1 meters. Well, 1 meter. Yeah, actually, yeah, usually I design for quizzes, okay, in-class quizzes. So the numbers would be very, very simple, very nice, easy to calculate. So wavelength is 1 meters. Okay, so now let's plug in the condition and see. Right, so now 2 pi, I'm just applying this, 2 pi divided by 1 meters times delta R 3 meters plus inherent phase difference pi. And so now let's calculate. So it will be 6 pi plus pi, 7 pi. And at this point, again, I warned in the recitation classes, be careful, because at this point, lots of students just see, it looks as simple as this part. They call it, okay, constructive. No. Slow down, right? Look, we're getting odd number of pi's. And for constructive interference, we have what? Integer, m, 0, 1, 2, 3, 4, 5, and so on. Integer times 2. It doesn't matter which integer. If you multiply it by 2, you're supposed to get even number. Even 2, 4, 6, 2, 4, 6, 8, and so on, right? But we're getting odd number. So it's impossible. It's impossible to get this out of that. So it's definitely not a constructive interference. So careful at this point. Don't rush. So it looks like either this or maybe something in between. So, but let's check. I will just rewrite this over here and see which m can fit. Right, so m plus 1 over 2 times 2 pi. Okay, m, again, you remember it's a 0, 1, 2, 3, and so on. Okay, let's start one by one. 0. 1 over 2 times 2 pi, it's just pi, not hour. 1, it's a 2 over 2 plus 1 over 2, it's a 3 over 2 times 2 pi gives us 3 pi, not our case. So next one, 2. 2, it will be 4 over 2 plus 1 over 2, it's a 5 over 2 times 2 pi, it's 5 pi, still not our case. 3, it's a 6 over 2. 6 over 2 plus 1 over 2, 7 over 2 times 2 pi, 7 pi. So this works. So m equals 3. So yeah, this condition matches. Oh, this matches that condition, right? So it means that at that point, that guy is going to detect nothing, just a noise. Destructive interference. So we're getting destructive interference. In case of acoustic waves, of course, just nothing except maybe ringing in the ears. And again, most of the time troubles are in the inherent phase difference, especially if students don't come to classes. There's just lots of just nonsense, right? And here occasionally, right, identifying which condition, but not often after me warning you many times. So usually students careful. And what else? No, that's it pretty much, right? So mainly in the inherent phase difference. So now, next, what's left? Yeah, maybe I will discuss this. Yeah. So these are semi-conceptual problems. Semi-conceptual. 2 circular waves. It's similar to what we discussed like 2 or 3 recitation classes ago, right? So I will put the first bullet, but I just want to remind that. Again, damn it, I have to draw a nice picture. So we have 2 waves, circular waves. Right, so you remember that. So let's say this is source number 1. And source number 2, let me draw it here somewhere. Right, so source number 2. So again, we assume that they are identical, so the same wavelengths, the same frequency, and the same wavelengths, and the same wavelengths. Right, so and 2 points are given. Yeah, of course they overlap, and of course they interfere. And 2 points. Let's take, for example, point which, let's say this point, or maybe let's take this point. Which point? Point A. And the second one, let's take this point, B. So we need to say what will be the amplitude of the net field at this point and that point. So we assume that okay, let me write amplitudes of, okay, the first wave. And you know what, now I don't like my the way I labeled my points, because we have small a for the amplitude, right? And now I have also small a here. Okay, it doesn't sound good. Let me change it to, for example, point C and point, oh no, C and D at the constructive and destructive. Damn it, so many different meanings, right? QR, okay. So let's assume amplitudes of this wave and amplitude of that wave exactly the same, and which 1 meter, for example, right? 1 meter. Can be ripples on, okay, 1 meter, not ripples, right? Almost storm. All right, so but anyway, amplitude of the net displacement at point Q and R. So, so we need to find amplitude of the net field. Let me write field at points Q and then point R. Net field, if it's in the case, if these are, for example, radio waves, or if it's ripples on water, of course, this will be just displacements of particles, right? Water molecules from the equilibrium, right? From the equilibrium. So discussions are very simple. You remember how we call these lines? These are wave fronts. Wave fronts are collections of crests. So it means that over here we have a crest, then trough, then crest, then trough, then crest. And the same about blue again. So we have, we can say that here we have crest, trough, and again crest. Right. So look, at point Q, we have intersection of wavefront, black wavefront, and blue wavefront, right? So basically, we have crest, blue crest over black crest, right? So if we have crest over crest, of course, at that point, amplitude is going to be doubled. It will be doubled, right? Amplitude of the net field is doubled. So it's if amplitude of one wave is 1 meter, so amplitude of the net field or net wave at that point is 2 meters, right? 1 plus 1, because we have crest over crest. So in that case, amplitude at point Q is 2 meters. As simple as that. Right? Now, point R. So what do we have here? It lies on the black crest. So it means that we have black crest at point R. And it lies between, in the middle, between blue crest, between two blue wave fronts. Basically, it lies in the crest, blue crest. So we have black. I have crest trough. Okay, it lies in the blue trough. Blue trough. Okay, getting late, right? So of course it lies in the blue trough. So we have black crest, blue trough. Of course there will be complete cancellation, so they're going to kill each other. Right? Again, black crest and blue trough. So at point R, complete cancellation, destructive interference. So the amplitude is going to be 0. Very simple questions, right? Occasionally I give a problem like this. Right, something similar can be in this form. Similar question. Look, these are circular waves or spherical waves in three-dimensional case. But what if you let this wave, this circular wave, what if you let it propagate to infinity? What if we let this wave go to r goes to infinity, right? So what are you going to see? Strictly speaking, of course, you're still going to see circular waves, but the radius of this circle are going to be infinite. So effectively, you are not going to see any curvature, right? So you're going to see basically straight line. And you remember actually from geometry, what is the circle with an infinite radius? What is a circle with an infinite radius? It's a straight line. Or a straight line, it's a circle, or we can say a straight line, it's a circle with an infinite radius. Right? So if you let this circular wave propagate to infinity, you're going to see these wavefronts in the form of parallel lines, which are crests, right? So you're going to see something like crest, trough, and so on. Right? So these are called plane waves. So these are called plane waves, right? But again, all these ideas that we used for circular waves can be applied here if you have plane waves. So now, if you have this plane wave interacting with the second plane wave which came from, from that direction. So let's say this, okay, let me show the direction of this plane wave. So this propagates that way. And let's say the second plane wave propagates this direction. So we have interference of two plane waves. So now if I ask you, for example, what will be the net displacement of whatever medium, maybe water, at this point, let's say point S, right? So what will be the amplitude at point S? Okay, so maybe I will write over here. So again, S, right, amplitude. The same story. We have wavefront, blue wavefront versus on top of a black wavefront. So it means crest over crest. So amplitude will be doubled. So amplitude at that point will be 2 meters, like here. But if we take, for example, this point, for example, this point. So S, I don't know what point, P. So what do we have here now? It lies on a blue wavefront. Basically, it means blue crest, and it lies between two adjacent black wavefronts. So it means that it lies in the black trough. So again, we have blue crest versus black trough. So complete cancellation. So we're going to get zero displacement of whatever water molecules, for example, at point P. So it will be 0 meters. So usually these questions, most of students answer them correctly, right? Because idea about the wavefronts, crests, and so on, quite straightforward. Reasonably simple. Okay, so what's left? So we started not at 4:30, we started almost at 5, 2.5 hours, actually not bad. So now let's discuss diffraction grating very quickly, right? Just to refresh. Although it's we just discussed it like in a previous week. And then a couple of problems, or maybe one about array optics. Basically, law of deflection and Snell's law. That's it. And most of you discussed that even in high school. 6, problem 6. Okay, I will write, so now it's a diffraction grating. So what do we know about that? Actually, not much about diffraction grating itself. Right. We know that it's illuminated by 2 laser lights. Right. So a red light, the wavelengths, let me label it as lambda, which way? I think subscript r. Yeah. Lambda r equals to 632.8. Oh my God, who needs this accuracy? Okay, now, just now I thought about this. But anyway, so that's the wavelength. And it creates second-order fringes, a fringe at a certain angle. Okay, now it's time to start drawing in order to see what I'm talking about, of course. Okay, I will draw it here underneath. Right, so let's say this is our diffraction grating. Right. And it's okay, yeah, let me draw also the screen underneath. So that is the screen. And distance, again, not given. Then let me draw the center. Right. And first, it's illuminated with red light. So lambda sub r. Right. So this creates its own interference fringes. So of course, at the center, again, there must be bright spot, which corresponds to m equals 0. So these are integers for red light. Then there will be over here somewhere the m equals 1, m equals 2. Okay, it should be weaker. M equals 2, and then maybe over 3. M equals 3 over there somewhere. Then let's say these and that. So this m equals 1, m equals 1, this is m equals 2, and m equals 2. Okay, so what is given? Angle is given. 2, I think the second. Yeah, the second order fringe. Second order, m equals 2. Okay, I will use red. Everything is related to the red color. I mean the red light. So this is what? Let me label it as theta 2 upper script r. Upper script r again stands for red light. 2 subscript upper script r. Right, and that angle is given theta 2 upper script r equals to, what's the angle? 53.2 degrees. Oh my God, so such a high accuracy. Then, yeah, I showed that angle. Then there is an unknown light. Okay, let me use blue. So, lambda x, unknown light, which we need to find actually. Basically, we're going to try to use it as a spectrometer. Right, and lambda x, which is unknown, we need to find. It creates its own interference pattern, and again, it doesn't matter which light you use. At the center, there must be a bright spot. M equals 0 all the time at the center. So this will be m equals 0. And then, of course, m equals 1, m equals 2 fringes corresponding to unknown light. So let's say this is m equals 1, over here m equals 1, and then over here there will be some m equals 2. Complete symmetry relative to the center. Right? Okay, somebody ask something. But still it doesn't show me on the chat, in the chat, your question. No, it still shows me the question which I already answered. Okay, stupid system. Forget about it. So that angle is 20.6 degrees. So this is unknown light and the first fringe of x. So theta subscript 1 upper script x in the parentheses. I think that's how I label it, yeah. And the angle is 20.6 degrees. Yeah. So in the question, of course, you see this wavelength. So first of all, diffraction grating. No, I need to show the angle. This angle is given, right? So this is theta 1 upper script x. That angle. Of course, it's exactly the same over here, but in order to sort of move them apart, this angle, so I drew different sides. Use different sides. Okay, so diffraction grating, two formulas, right? Because this time, you see angles are far from being small. So here, we managed to combine these two formulas and write this expression, this formula, because in a double slit experiment, angles were small. But in a diffraction grating, angles are not small. And you can see 20 degrees. You never can call 20 degrees as a small angle. Right? So that's why we have to use both of these formulas. But, okay, let me first rewrite them, and then I will discuss d sine theta m equals to m lambda, right? Ym equals to L times tangent of theta m. Again, the meaning of these formulas. The first one gives us angles to the bright spot, 0, 1, 2, 3, and so on. So this gives us angles. This allows us to make a transition from angles to distances along the screen. Okay, my neighbors now feel like listening to some music. All right, so, but look, in our case, angles already given. Right, angles are given, so all information is in angles. And the wavelength is also here. So it looks like the second equation in this problem is not even needed, right? Because somebody was managed to measure angles. So in this case, I can write that this, in our case, it's not needed. It's not needed. So the second equation is not needed. So we can just play with the first equation only. So let's write for this fringe unknown light and this fringe of red light. So let's write for red. So d sine of theta. Okay, which theta? This is the second order fringe, m equals 2, so I will put theta 2, right? And, of course, upper script r stands for red. And, okay, m equals 2, so here 2. 2 times lambda, of course, subscript r. Then, for unknown light, since they interact with the same grating, so d is the same for both lights, right? I can write, so the same d sine of theta 1 unknown light equals 2. So now m equals 1, so this is 1 times lambda x. So now we can take either ratio of both these equations to get rid of d and solve it for lambda, but let me do it without taking a ratio. So from the first equation, I can get d because lambda r is given. angle is given, we can get d, and then plug it in the second equation and get lambda x. Right? So basically the solution. Right? Okay, so let me solve it for d. d equals 2 lambda r divided by sine of theta 2 sub r, I mean upper script r. And as I said now, we can plug it into the second equation. Right? And here, it's already lambda x, 1 times lambda x, so this is our unknown. So lambda x equals, instead of d, this, do 2 times lambda sub r divided by sine of theta 2 upper script r, and times sine of theta 1 upper script x. So problem is basically, yeah, it's a very simple problem, right? Okay, I'm not going to plug numbers. I will just write down the answer. Again, this is what 20 degrees, 20.6. This is 53.2, and the wavelength is 632.8. So the answer will be 553.7 nanometers. I don't know exactly what color. 400-ish, it's blue, 750 red. Okay, around that. So this is somewhere in between, right? I don't know. Greenish, yellowish. I don't know exactly. I don't remember. Okay, simple kind of way of finding frequency of an unknown light. Okay, double slit. We'll skip, right? It's even easier, just one formula, right? So you don't have to play with two. And yeah, we just discussed it in the previous week. Array optics. We did not have recitation classes, right? So we just discussed it in the lecture. So let me just solve a couple of problems. Right? Most of the time it's geometry and Snell's law. Geometry, you're familiar with geometry from high school. Right? Working with the properties of right triangles and so on. Okay, now I need to clean this part. Can I? Any questions? Yeah, it's still the same. Again, guys, if you need more explanation and clarifications, right? Okay, I will keep the last couple of lines. So this should be problem number 7, I think. So now that's array optics. We have a prism made of something. Okay, probably something like glass. But we will have to find index of refraction. This index of refraction, probably I should have framed it because it's one of these essential parameters in optics. C over V, right? So we will have to find index of refraction. So what is given? We have a prism of this form. I'm trying to estimate the amount of space I might need on that side. Okay, it should be enough. No, let me make it, draw it like this. No, it's too much. And close to the previous one. sort of triangular prism. This is 90 degrees. At this angle, 60 degrees. And this angle obviously must be 30 degrees. Right. This angle, for example, there's no point of giving. We could deduce that. Then, here, outside of the prism, it's air. So index of refraction is 1, right? Because in air, light propagates almost with the speed of light. So with a very, 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 very good approximation, we can use speed of light in air. So here we have air, and index of refraction, let me call it N1 is 1. Then, as I said, in the prism, N2, we need to find index of refraction of the prism. Then, some information about a ray is given. One ray is shown. And that ray propagates this way. So let me hit it here. So it hits this surface at this point. Okay, let me write. So this is ray. Some additional information is given over there, but first let me discuss with you what happens to this ray at this point, and how is it going to propagate in the prism at this interface between the glass and air. Of course, from everyday life, you know that this ray will go straight, will continue flying straight, right, like this. But let's get that from the Snell's law, because what happens at this interface? Diffraction. Of course, a little bit of light will be reflected, but most of light will get into the prism, and it will propagate still along the same direction. Why? From the Snell's law. Okay, I just know at some point students tend to make one simple silly mistake. Okay, I will erase this, and let me label this point as point. Let me use blue. Point A. Point A. Right. So let me over here discuss point A. Again, it's not completely related to the problem, right? We can solve it without discussion, right? Because you know how it is going to propagate. But anyway, point A. So let's apply Snell's law. N1 sine of theta 1 equals to N2 times sine of theta 2. And I want to ask you, what's the value of theta 1 for this incident ray? That's where students make mistakes. If I ask, for example. Because very often students see, it's perpendicular to this boundary, so theta 1 is 90 degrees. No. Why? Because you remember how we define directions of these rays. We measure angle from what? From the normal line. This, you see, it's an angle between the ray and the normal line. In this case, at that boundary, normal line is along the ray. So what's the angle? Theta 1? 0. In this case, theta 1 is 0 degrees. Of course, kind of after explaining, of course, everyone, yeah, of course, it makes sense, right? But of course, if I let students do it by themselves, lots of mistakes will be at this point. So you need to get used to the idea that the angles are measured from the normal line. Of course, after some time, it will be in your head, right? And then, of course, as a result, so a sine of 0 degrees, of course, 0. And it means, as a result, theta 2 must be 0, right? Here, of course, we can say that theta 2 equals 0, must be 0, right? So that's why. So if theta 2 equals 0, it means that this ray propagates in the prism, still propagates along the normal line, right? So that's basically justification of the fact that the ray still propagates along the same direction using Snell's law. Right? Again, it's not it's not totally related to what is given in the problem and what needs to be found in the problem. But I felt like it's worth of discussion. Okay, let's call this related to the direction of that ray. Okay, and now we can actually start discussing problems. You know what? Let me sort of separate it. It's a digression. Okay, so now back to the problem. So now ray hits this surface at the angle. And we know, of course, there will be a refraction. Of course, there will be a refraction, which is which can be described, or which is described by the Snell's law. And we know that after refraction, this ray will propagate this way. And we know one angle. This is the line horizontal along this ray, right? So, and this angle is given. It's phi equals to what? 25 degrees. That's it. That's the problem. Okay, statement of the problem. And what we need to find? We need to find index of refraction. Right. Again, if I remember, if I give a problem like this, not many students manage to get through the geometry, although geometry is at your level, but we have to arrange it properly, all the geometry. And again, then at the end of the day, we will have to use Snell's law, because that's the physics which describes refraction. Okay, so let me write. First, let me label this point now as point, for example, B. Right. So now about point B. Of course, refraction at point B. So at point B, of course, I will have to apply Snell's law. So N2 equals sine of, you know what? In my notes, okay, yeah. I was just thinking about indices. Anyway, so it's fine. So this is glass. We use subscript 2, so N2 sine of theta 2, and equals to N1 sine of theta 1. And again, it's at point B. That was about point A. Now it's about point B. Let's see these angles, theta 1 and theta 2, because we need to understand what needs to be found, right? Because N1 is given. This is our unknown. Okay, let me emphasize. So this is our unknown. So this is given, theta 1 and theta 2. That's what we need to understand, get some information about these two angles. But first of all, let's draw them. Let's see them on the figure. So since angles are measured from the normal line, we must draw a normal line, or the normal line at point B. Okay, I will use green. So perpendicular, so okay, let me emphasize. So this is normal line, right? Okay, now what is theta 2? It's in the glass, angle in the glass. It's like this. Okay, so this is normal line, this is ray, so that is theta 2. You see? Between the normal line and the ray, and the ray, this, normal line this, so that is theta 2. Now, theta 1, so this is normal line, this is the ray. So the angle is that. Okay, let me put it here, so it will be this. Okay, I need to start the camera. So this will be our theta 1. So now, after realizing where those angles, so now let's somehow find one of these angles. Okay, before we start discussing, look, what can you say about, for example, this angle, theta 2, and this angle? Are they the same? They should be. because it's an intersection of two parallel lines. So this line of rain, it's a horizontal line, you see. And this line, it's a normal line. Intersection of two parallel lines. Of course, these angles are called the vertical angles. So, of course, this is also theta 2. We will need it, theta 2. So, as a result, theta 1, I can connect with theta 2. Theta 1, you see, it's this big angle. It's a theta 2 plus phi. Okay, let me rewrite it because it takes too much space, and I want to squeeze that piece of information. So, theta 1 equals to theta 2 plus phi. You see, it's simple geometry, which you learn in high school, most likely. And now, let's move. So, let's look, for example, at this triangle. Let me label this point as, let's call it C. Now, let's look at the triangle A, B, C. You see, A, B, C. Is it a right triangle? Of course it is, because this ray is horizontal, perpendicular to this boundary, so this angle is 90 degrees. So if that angle 30 degrees, of course this angle is 60 degrees, which is equal to that. So this angle is 60 degrees. Equals to that one. So we can say that angle A, B, C is 60 degrees. And now the rest is trivial. If this angle is 60 degrees, then this angle between the boundary and the normal line, you see this angle is 90 degrees. So angle theta 2 and angle 60, you see theta 2 and 60, they complement each other to 90 degrees. Right? So 60 plus theta 2, 90 degrees. Right? So it means that, okay, also I can write so that, yeah, I said theta 2 plus 60 degrees equals to 90 degrees, right? So as a result from here, we can get that theta 2 equals to 30 degrees. Theta 2 equals to 30 degrees. So this is 30, that. And we just connected theta 1 with theta 2, and phi is given. So we can find theta 1. So then theta 1 equals to theta 2 plus phi. Right? So theta 2 we just found. It's 30 degrees plus phi is 25 degrees equals to 55 degrees. So now we found theta 2. Probably I should frame it with, right, because these are important, and 55. So plug them. And we can solve it for N2, N1 is given. Right? So now back to Snell's law. So N2 sine of theta 2, 30 degrees, equals to N1 sine of 55 degrees. Right. Yeah, N1 equals 1. Maybe I can write immediately here, it equals to 1. So this equals to 1. Right. Okay, so from here, N2 equals to sine of 55 degrees divided by sine of 30 degrees. Right? It looks like, yeah. So that ratio gives you 1.64. There are no units for the index of refraction, because what are we dividing? Speed by speed. No units, it's unitless. Right? So just 1.6. Usually the index of refraction of just a regular glass, 1.5, so it's slightly more than that. Maybe some kind of glass, special type of glass. Again, from the point of view of physics, it's quite straightforward. You just need to apply Snell's law, nothing else. But geometry, yeah, you have to draw carefully sometimes, so sit and stare for sometimes in order to see geometry. But with geometry, that's all the time like this, right? So sometimes even graduate level students can draw the picture and then stare for quite some time in order to understand how to handle with these angles, directions, right? So that's geometry. Right? From the physics point of view, from the point of view of physics, Snell's law, nothing else. Right? And of course, don't forget that these angles, theta 1, theta 2, measured from the normal line. It's another place for mistakes, unneeded mistakes, unnecessary mistakes, but it happens. You said about why we're getting that this angle is 30 degrees?
Right.
Geometry. Look, again, no, I need a marker. So this is horizontal. This is perpendicular to this line. Then, so I guess you don't have problems with understanding why this angle 60 degrees, right? Don't you?
Right.
Yeah, because yeah, it's basically equals to that by just geometry. Or you can, as I said, you can look at this triangle ABC. This is 30 degrees, this is 90 degrees, that this is angle 60 degrees. This is 60, and you remember that this is horizontal, then this is perpendicular, right? So it means that this angle, you see this angle?
Yep.
90 degrees. That angle between this normal line and this line perpendicular. And this 90 degrees angle consists of two parts. Look, just by geometry, right? So above red line, 60 degrees angle. Below this, theta 2.
Yep, that makes sense.
So this angle plus that angle gives us this angle 90 degrees. Of course, it makes sense because it's simple, but you just need to see it. That's why I told you, right? So, and there's no recipe how to make it faster, right? How to come up with the right conclusion. It's geometry. You just need to sometimes sit and stare, right? I know my own experience. Right? And even sometimes still that can be reasonably slow. Right? Yeah, that's not physics, it's geometry, right? So yeah, so this angle plus this, they complement each other to this 90 degrees angle. So it means that this theta 2 must be 30 degrees. 30 degrees, right? So that's what I wrote it here. Right? And so then I solved it, of course. No, here I solved it, of course, for theta 2, 30 degrees. Have I answered that question?
Yes. Yes.
Yeah,
Thank
you just need to see it because yeah, lots of line, lots of angles, as I said, that's why you just need to close your ears, right, and stare for some time in order to see it, right? Right. And of course, yes, sometimes if person who knows just give you a slight hint, right, and then it triggers and you start seeing almost everything. So, yeah, I understand your question because yeah, I've seen even in the graduate level students the same response sometimes. Of course, not with this geometry, slightly more complicated. All right. Okay, guys, so the next problem, maybe let's also discuss it. It's about, again, array optics, again, Snell's law, basically, nothing else. Of course, if I give a problem about ray optics, it will be something, it shouldn't be complicated. Shouldn't be complicated, right? Just, again, simple geometry plus Snell's law. Even this, if I give a problem like this, there will be lots of troubles. There will be lots of troubles. But that's how we learn it, right? We all struggle right? When we were students. Okay, so let me start erasing this. And the next one is simpler. Right. And again, justification of this, what happens at point A, there was no need. But again, I wanted to emphasize on how we measure these angles, because some students miss that point. So now this should be problem 8. And this will be the last one. Oh, wrong color. But anyway. So we have now a glass plate. And yeah, we will have to index of refraction of the glass again. Right. So we have, okay, let me write glass plate. And oh, maybe I will use my ruler. Right. And I don't want the rest, so it should be enough. Okay, maybe I will just use this if it's not confusing. Okay, just trying to make sure that this is a different material. So above it's air. All right, so let's say this is air. So N1 equals 1, of course. And probably I need to write it on the other side. Air, so N1 equals to 1. And here, some kind of glass, and we need to find the index of refraction. So here, some kind of glass, N2, and that's what we need to find. So what is given? So there is a ray incident on this surface. Incident ray. Of course, there will be part of this light will be reflected, right? And part will be refracted. All right, so it will get inside. And what is given? Now, first of all, the angle of incidence is 60 degrees. Angle of incidence, in order to draw it, we need to draw a normal line. Actually, I will use black this time. So again, this is normal. So angle of incidence, it means this angle. Theta 1 is given. So theta 1 equals 60 degrees. Then second piece of information is this. What is given? That this angle between this ray, reflected ray, and refracted ray, this angle is 90 degrees. They are perpendicular to each other. Okay, it happens. So the angle between reflected ray and refracted ray, the angle is 90 degrees. So let me write it down. Maybe I should probably write it in words, maybe. The angle between, between okay, let me use the refracted, the reflected and refracted ray. Rays is 90 degrees. Okay, so we need to find index of refraction of the glass. So what we need to find? N2. Again, in terms of physics, again, we will have to use only a law of reflection, which tells us that angle of incidence equals to the angle of reflection. It means that this angle is also theta 1, right? So it means that this angle also theta 1. So basically, immediately I use the law of reflection, right, first. And then law of refraction must be used, which is Snell's law, right, carefully. So second part, Snell's law, right? So which is that is 1, so it's n1 sine of theta 1 equals to n2 times sine of theta 2. Again, that is our unknown, right? So this n1, it's air, so it's 1. So no troubles this. So we need to find out what is theta. Oh no, theta 1 is also basically given. Not basically, it's given. All right, so this is 60 degrees. So we just need to figure out what's the story with theta 1. Right. And again, let's first show it on the diagram. Where is that theta 1? So obviously that theta 2. It's the angle again between the normal line and the refracted ray. Okay, I didn't show its direction. And the refracted ray. So that's theta 2. And so we need to add an additional equation in order to find or get some information about theta 2. And again, geometry. We just need to stare at that equation, at that picture for a little bit. Even when I was preparing for the class, right, I solved this problem several years ago, and I haven't used it for quite some time. So I need to stare. So what's the geometry? It's normal. And of course, I will tell you the story. Look at this big angle. From this point, you see, from that direction of the normal line, all the way to this direction of the normal line, to this open angle, which is 180 degrees, right? So you see this whole angle is 180 degrees, which consists of 3 angles, theta 1, 90 degrees, plus theta 2. That's the key part of the picture. That's the key part of analysis, geometrical analysis. So you need to see that these 3 angles, this plus this plus this, they create angle over 180 degrees. You see that? You should. So just from the picture, we can see that theta 1 plus 90 degrees plus theta 2 equals to 180 degrees. Okay, let me show that 180 degrees angle. It's this big angle. You see, 180 degrees. Right? So that's an additional equation, which will allow us to find theta 2. So look, theta 1 is given 60 degrees. This is 90, so we can solve it for theta 2. And then plug it here, and using Snell's law, we can find n2. Again, you see, just geometry. Physics is simple, just law of reflection and Snell's law, they're reasonably simple. But yeah, problems like this, troubles are in the geometry. So of course, from here, we can, so this is of course 60 degrees, let me emphasize, so this is 60 degrees. And then underneath, I can write, so of course, theta 2 will be equal to what? This will be 150, 30. Theta 2 must be 30 degrees. Is 30 degrees. So 30 degrees is correct. Yeah, 30 degrees. So now, yeah, we just need to plug it and solve it. So Snell's law. So this is 1 times sine of, okay, let me write theta 1 equals to n2 times sine of theta 2, right? So we need to get this. So n2 will be ratio of sine of theta 1 divided by sine of theta 2. So it's a sine of 60 degrees divided by sine of 30 degrees. Sine of 30 degrees is 1 over 2. Sine of 60 degrees, square root of 3 over 2. Again, when I was an undergrad student, our professors used only these angles 0, 30, 45, 60, 90. As a result, I remember it. I remember them by heart, the values. So of course it will be square root of 3 over this square root of 3 over 2 divided by 1 over 2, so it will be square root of 3. Okay? That's why I'm still thinking about giving a problem about ray optics on the exam, because again, physics shouldn't be complicated. It's geometry, but geometry again, it's a high school. Okay, so that's what I was planning to discuss.